So the kilojoules of heat that it started off with was 4.2 or 42.8 kilojoules.
Okay.
And the temperature rise is 68.6 degrees Celsius.
And the specific heat is 0.385 joules grams degrees Celsius. Right, so the first step, because our specific heat capacity is given in joules per gram. I love how people jump in the chat and like tell me to do more questions as I'm already doing questions, like it's going to change anything, right? 42.8 kilojoules. I've got a list of like 10 questions I'm working off of, so you can hold on to those questions for a little bit longer. Right, 1,000 joules, 1 kilojoule. So that's the first step. I would convert energy to joules because our specific heat is in joules as well. So multiply that, right? We get 42,800 joules in total. Now I jump to Q equals MC delta T. So my Q, 42,800 joules. My mass is my unknown component, and my specific heat 0.385 joules grams degrees Celsius, and my delta T 68.6 degrees Celsius. So divide that across, let's see, 42,800 divided by so I get a mass of right, like 1620.5 grams, blah, 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 blah. Oh, okay. They ask for what's the mass in kilograms. So, right, the original mass would be in grams because our specific heat capacity of copper is given in grams. So the last step, right, would be, we know 1 kilogram is 1,000 grams. So we divide by 1,000 to get 1.62 kilograms of copper. I would say 3 significant figures because energy was 3 sig figs, my delta T was 3 significant figures, so I would go with 3 significant figures on this answer. So 1.62 e to the 0, right, kilograms of copper for question 41.
Thank you.
Yep. And let's see, we had 43, 44, 46, 47. All right, question 34. Yeah, sorry. It's somewhere here. There we go. I didn't write down the other questions, so I was just getting that. See, 43, who's got 43 for us? Oh, this is we're all set with 41? How did you get the mass there? 2 hot pockets. All right. That's our unknown, right? That was what we were solving for. They gave us the energy that was put in. They gave us specific heat capacity and delta T. So mass was our unknown. So I just divided across the product of my specific heat capacity and my delta T. And that got us a mass in grams. They asked for the mass in kilograms. So I had to just do a unit conversion to go from grams to kilograms. All right, Hot Pockets. All right. Yeah, I had Guy Fieri joined a Zoom session once. Felt very, very flattered that Guy Fieri came to a chemistry review session. So how many grams of zinc do we have in this reaction?
I have 1.16 e to the negative 1.
1.16 grams of zinc. And then what's your volume of HCl?
5.21 e to the 1 milliliters.
And blah 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 blah. And then what's your delta T? Or what's your temperature?
23.4 degrees Celsius to 24.6 degrees Celsius.
So our delta T is what, 1.2 degrees Celsius? Yeah. So they want the heat of the reaction in kilojoules per mole. So we're going to start with the water, right? The water, because that's what we're measuring. We're measuring the water. So Q for the water, right? The mass of water, basically water is 1 gram per milliliter. So I have 52.1 grams of water, 52.1 grams. Specific heat of water is 4.184 joules, grams, degrees Celsius. And my delta T is 1.2 degrees Celsius. Multiply all that together, and I get the heat that the water absorbed. So 52.1 times 4.184 times 1.2, right? So the water absorbed 261.58 joules of energy, right? So that means the reaction, right? Q for the reaction is opposite of that. The reaction lost 261.58 joules of energy because the water was able to absorb that energy. So the last step to basically find the heat of the reaction, right? Just look at the units. The units they're looking for are joules per mole. So we want to figure out how many moles, of zinc we have in this reaction. So we go and look up zinc. I think zinc is 65.38 grams per mole. Well, I've got 0.116 grams of zinc, and I know for every 1 mole of zinc, I need 65.38 grams of zinc. So 0.116 divided by 65.38, 0.00177 moles of zinc, right? We're looking for the heat of a reaction. It's usually in kilojoules per mole, but in this case, they're just asking for it in joules per mole. So, all right, the reaction released 261.58 joules, and that was when I had 0.00177 moles of zinc react. I divide those two, and that should be my answer. So 261.58 divided by that, I get a giant number, right? 147,431 joules per mole. Like I said, they're normally given in kilojoules per mole because they're usually a large value. So let's see, significant figures. I would personally go with 2 significant figures based on the delta T, the change in temperature. There was 2 significant figures there. But looking at the back end of the top hat question, they've got it set to 3 significant figures for some reason. So I would say 1.47, right? E to the 5 joules per mole. And that's a negative, right? Because our heat released was negative. So again, your numbers might not have been exactly the same, but the steps would be the same for question 44. All right, so we did question 41, we did question 44. Did I do question 43? I did. Yeah, I did question 43. All right, 46 and 47. Oh, I did question 47 already. That was the first question we did. So just 46. And then I'll take a look at 34. We're all set with 44?
Yes, thank you.
All right, so let's see, HQ 5.46. Right, another Hess's law. I've got 4 moles of iron, 3 moles of oxygen, yield iron 3 oxide, and the delta H for that reaction is 1648 kilojoules. And then I've got 2 carbon dioxides, break down to 2 carbon monoxides plus oxygen, and the delta H is 565.4 kilojoules. The reaction we're looking for, right, is iron 3 oxide plus 3 carbon monoxides yields 2 elemental iron and 3 carbon dioxide. So quite a lot going on in here. 2 things, right? We have to do 2 things to the first reaction because I want the iron 3 oxide as a reactant and I have it as a product. I also want 1 mole. I currently have 2 moles. So I've got to flip this and I have to divide it by 2. So I flip that, I get iron 2 oxide yields 2 iron and 1.5 oxygen. This becomes positive, and that would be 824 kilojoules because I had to flip it. The sign becomes positive. I had to divide it by 2 because I divided the whole reaction by 2. The next one is also kind of complicated because we want to have carbon monoxide as a reactant. I have it as a product. I also want to have 3 moles of it. I only have 2 moles. So the second one's a little weird in that we're going to flip it and we're going to multiply by 1.5. So that gives me 3 moles of carbon monoxide plus 1.5 moles of oxygen goes to 3 moles of CO2. And I'm going to multiply the delta H by 1.5 as well. So let's see, 565.4 times 1.5. And I get a negative 848.1. Now I can add those 2 reactions together and oxygen disappears like I need it to. And I'm left with iron 3 oxide plus 3 carbon monoxide yields iron and 3 carbon dioxide. And I'm left with, right, 24, 0.1 kilojoules as the delta H for that reaction. So we should have, because there's no decimal places in 824, we shouldn't have any decimal places in the final answer. So we should report the final answer as just negative 2.4 e to the 1 kilojoules for question 46. All right, Hunter wants us to go back to question 47, and then I'll do question 34, and then I'll jump into the practice exam. All right, question 34. Oh, okay, yeah, 34 is kind of similar to some of the other problems we've done tonight. So HQ 5.34. All right, 0.1625 grams of magnesium. We burn it in the bomb calorimeter. The heat capacity of the bomb calorimeter is 3.03 kJ per degree Celsius. Temperature increases by 1.252 degrees Celsius, right? They're looking for the heat of the reaction. In kilojoules per mole. All right, so Q for the calorimeter is C delta T because they give us the heat capacity of the calorimeter. So Q for the calorimeter, the specific or the heat capacity of the calorimeter, 3.03 kJ per degree Celsius, right? Delta T, 1.252 degrees Celsius. So Q for the calorimeter, multiply those two together, 3.03 times 1.252. I get 379 kilojoules. So what does that make my Q for the reaction? Right, has to have the negative sign, the opposite sign. The reaction lost that energy because the calorimeter absorbed that energy. And then the last step, right, they're looking for kilojoules per mole. So, all right, I've got 3.7935 kilojoules. I've got what the hell? Just a second here, something's. I hit the wrong button. We've got Q, gotta find our mass and our moles, 125 grams. So why do we not worry about mass in this problem? Because they give us the heat capacity of the calorimeter, right? The heat capacity of the calorimeter is just for the total calorimeter requires this much energy to heat it 1 degree Celsius. So it doesn't matter, like Mike said, right? It doesn't matter the mass, it's already included in the heat capacity of that calorimeter because we're heating the whole thing. We're not heating it by gram or per gram. So I got to find moles of magnesium, right? Let's see. Magnesium is 24 grams per 1 mole. So 0.1625 divided by 24.31, get 0.00668 moles of magnesium. So the same as I did before in that previous problem we did, right? I've got energy. I'm just going to divide by my moles because I'm looking for kilojoules per mole. Right, so 3.7935 divided by that, and I'm going to get a negative, 567.5 kJ per mole. Take a look at significant figures here. And I'm going to say, yeah, we should be looking for 3 significant figures. So I would just say, that is really close. Yeah. I guess 568 negative 568 kilojoules per mole for question 34. And if they tell you that's wrong, I would go with 567. All right, we ready to jump into the practice exam?
Excuse me, I was just wondering why on that question, when it's